This fellow is a piratey sort of person. Forgot to button his shirt, and I don't know. I guess that's not a shirt. That's some sort of vest. So now we're gonna rename things. We've got that normal distribution, and we're gonna note that when we talk about a particular item, like randomly selecting a woman and measuring her height, or randomly selecting a bag of M&Ms, we're going to call that thing a random variable. So the variable is the item we're selecting. And our author's like, why? Because it's random and it can vary. Well, sure, right? Like we select a bag, and how we got that, I don't know what makes that bag random exactly. But what's in the bag can vary based on how accurate the machine was. So I guess that sort of makes sense. What we want you to know, and I kind of mentioned it already, is that those percentages under the curve, so these percentages are also probabilities. They're the same thing. But we already talked about that, right? We knew from 4.1 that percentages and decimals and fractions could all represent a probability, provided they were a value between 0 and 1, right? That's the key thing. They had to be between 0% and 100%. So the area under the curve, key connection here, area under the curve is equal to the probability. It's the probability of randomly selecting something with the same criteria as as the given values. So for example, here we're like, hey, if we randomly select a 1 pound bag of M&Ms from somewhere, from some pot of bags of M&Ms, what is the probability we get one between 529 and 541 M&Ms in it? Well, it's a 0.135 or 13.5% chance. Like both of those are probabilities. So it's somewhat likely that we'll get a bag that has that many M&Ms in it. That's what we mean by that random variable. Okay, well, it turns out that talking about different random variables, but wanting to compare their values can be challenging. For example, one of the standardized tests to get into college entrance exams is an ACT, the other is an SAT, and they have a completely different grading scale, like point scales. Like ACT, if I'm remembering correctly, is like out of 36 points, and the SAT is out of like 1,600 points or 3,200 points or something, right? And so, how could we know if we got two students that applied and one took an ACT and one took an SAT, who did better on the exam? Now, our author says, do we think these are normally distributed? Well, they are designed to be that way because they're standardized, right? It's controlled what is told to each student. Each question is supposedly carefully crafted so that all students have equal access to being able to answer the question based on the curriculum they went through in high school. I think that's the idea. Now, we can't compare their scores directly, so what we do is we compare them using what's called a z-score, and it's a way to standardize different data sets. And what the z-score is it takes a data value and it measures how far that data value is from the mean. So if we had the mean and then we knew the standard deviation and the data value was exactly equal to one standard deviation above the mean. In other words, if we selected a bag of M&Ms and it had exactly 529 M&Ms in it, that particular data value is exactly one standard deviation above the mean. Its z-score would be equal to 1. In fact, the z-scores, a z-score of a data value that was equal to the mean would be 0 because the distance between that data value and the mean is 0. There's no distance between it. And then above the mean would be 1, 2, 3. Below the mean would be negatives. -1, -2, -3. So key point, I think this is worth underlining and writing in your reference sheet. A z-score tells you how many standard deviations a data value is from the mean. It's a measurement of distance where the unit is standard deviations. Okay, so question 5 says, hey, what happens if a data value has a z-score of blank? Then half of the data are below that value and half of the data are above. Well, it'd be 0, right? Because that's the marker of 50% above and 50% below. This also tells us that the true center of a normal distribution is also the median, right? Because if we take the data set and we put them in order from smallest to largest and count to the middle, we find the median. But it turns out that when a data set is normally distributed, the mean and the median are approximately the same value. That's actually one clue to determine, hey, is this data set normal? We'll calculate the mean and the median. And if they're about the same, that's a good indication if the data set is normally distributed. So how might we calculate the z-score? Turns out there's a nice little formula. This is supposed to be sigma. I don't know if your textbooks have it misprinted. It's supposed to be sigma here as well. I think let's ignore that and let's just say that the z-score is equal to the data value, which our author is labeling x, minus the mean. And whether it's a sample mean or population mean doesn't particularly matter, divided by the standard deviation. And again, whether it's the sample standard deviation or the population standard deviation doesn't particularly matter. So here's an example. We've got a student that, we've got 1 year that the mean score on the SAT was 21.2 with a standard deviation of 5.1. That was for the ACT. The SAT had a mean score of 1060, standard deviation 95. So one student scored a 26, the other 1230. Who did better? We're supposed to guess. I don't know. Let's just say the ACT and see what happens. To me, I'm like, why would we do this when we were just told what the z-score is? Let's just do the z-score calculation. So what I'm going to do is I'm going to label ZA as the calculation for the student, the ACT student. Their data value, they scored a 26. That's their data value. We're subtracting from them the mean of 21.2, and we're dividing that by the standard deviation of 5.1. We'll calculate that in a second. The z-score for the SAT student, we're going to type in their data value, or write their data value. That's 1060. I'm wrong. That is the mean score for all students. That's the population mean. This student scored a 1230. Oh, that's above the mean. Good for them. The mean score for that year was 1060 with a standard deviation of 195. Okay, let's get our z-scores. We'll find these in Desmos. I like to set up the fraction from the get-go and do 26 minus 21.2 divided by 5.1. You don't have to. Notice our value here. You might be tempted to turn this into a percentage. It is not. This is 0.941 standard deviations above the mean is how you should write that. It's above because it's positive. All right? The other one, I'm just hitting the division button. We're going to do 1230 minus 1060. We're dividing that by 195. The ACT student scored 0.872 standard deviations above the mean. Let me show you what I wrote. So if we're comparing these two students, it turns out that the ACT score is slightly better because it's a little bit higher than the mean. In other words, 0.941 is a few standard deviations higher than the mean than 8.72. Not a whole lot, right? They're not widely different. They're both pretty close. The other thing to note is what's happening here is relative to all SAT test takers, this student was just 8.72 standard deviations above the mean. They're just a little bit better than the average test taker. And the same thing here, this ACT student, they're just a little bit better than the average test taker. Not even 1 standard deviation above the mean. One of my colleagues looked up the thing to get into Mensa. I don't know if you've heard of that. That's like this Society of Smart People or whatever. And to get into Mensa, you have to be, the cutoff is 2 standard deviations above the mean for your IQ test score. And there's online test scores you can take to determine your IQ. And if you're 2 standard deviations above the average IQ score, you can get into Mensa. Okay, so what exactly does each z-score tell us? The number of standard deviations away from the mean that each of those values are. Number of standard deviations, the data value is from the mean, and we already answered it. The ACT is the better one because it's a larger value. Because 0.92, 941 is larger than 0.872. We should be careful. It is not always true that we want the larger z-score. It's just in this context, the higher the score, the better. The better you scored.